Okay, good afternoon, everyone. My name is Mikel, and I'm going to present my capstone titled Securing Healthcare Internet of Things Using Quantum Key Distribution and Post-Quantum Cryptography. And so here's the roadmap for today. We'll move through the problem and objective. We'll go into the system design and methodology. We'll talk about the results, and then we'll close out with the discussion, implications, conclusion, and where this research can go next. So let's start with the problem. Healthcare Internet of Things is expanding rapidly via patient monitors, infusion pumps, AI wearable devices, neurostimulators, and network surgical systems. And these aren't just data endpoints, they're life-critical infrastructure. And the encryption that we currently have protecting them was designed before quantum computing was a credible threat. And so it wasn't built for them at this moment. And when the encryption fails in a hospital setting, the consequences are just a data breach, their incorrect medical data being transmitted, delayed critical responses, and patients whose lives are directly at risk. So it doesn't just make it a theoretical or cybersecurity problem, but a life-threatening problem. And so why this research matters, the encryption standards we rely on today, those like RSA and ECC, are fundamentally vulnerable to quantum computing attacks. It's not just a future concern anymore, it's becoming an active one as quantum computing evolves. And there are two promising solutions that exist: quantum key distribution, which is highly secure but unstable under real-world conditions, and then post-quantum cryptography, which is stable but built on mathematical assumptions that could one day be broken in the development of the quantum world. And so the gap this research aims to fill is the absence of an adaptive system that delivers both security and reliability simultaneously in a clinical environment. And that is the gap that this entire project is aimed to fill. So my objective was to design and evaluate a quantum resilient communication framework and to test three distinct approaches head to head. So the first approach will be the quantum key distribution, which generates encryption keys using quantum mechanics and detects eavesdropping through quantum disturbances. It's highly secure but sensitive to noise and channel instability. The second approach will be post-quantum cryptography, which uses quantum resistant algorithms and requires no special hardware, but scales across existing infrastructure easily. It's stable and consistent, but as far as security, it's only as strong as a mathematical assumption that hasn't been broken yet by quantum advancements. And so the third approach, which is the core of my research, is the hybrid quantum key distribution and post-quantum cryptography model. And this framework uses quantum key distribution when conditions are stable and automatically switches to post-quantum cryptography the moment the channel is compromised. It does this with no manual intervention, no packet loss, and no gap in protection. And the adaptability is what makes it different from anything that comes before it because it enables continuity of care. And so this is the system architectural blueprint of the framework. It's at the center of the design engine, and it's continuously reading the quantum channel and evaluating threat signals and routing between protocols in real time. And every IoT device in the network is protected by this layer without needing to know it exists, and operates silently and automatically without interruption. So you'll see here to the left that data is generated from AI wearable devices, whether it be heart rate or I don't know, glucose levels. And the end goal is to get data to medical service so medical providers can provide or make medical decisions. Behind the layer, you have QKD, which is the quantum layer, driven by the BB84 protocol. It also has the ability to detect disturbances such as man-in-the-middle attacks or eavesdropping. And when that's detected through it falls back to post-quantum cryptography, which is the second layer of encryption that uses a mathematical-based a framework. So moving on to methodology, to validate whether this framework actually is performed as designed, I simulated all three protocols in Python. I tested each of them under normal and adversarial conditions, and I introduced three attacks, those being eavesdropping via intercept resend, channel noise injection, and man-in-the-middle attacks. The metric that I used to track was the QBER, also known as the quantum bit error rate, the communication success rate, and then the post-quantum cryptography fallback activation rate, and the end-to-end latency, as well as intrusion detection rate. And the success criteria were clear. Those are based on the high success rates under attack, effective threat detection, and minimal unnecessary latency. If the hybrid couldn't outperform the individual protocols under pressure, the added complexity would be justified. So I designed a simulation to be rigorous enough to prove or disprove that exactly. So just going into the security logic, here's the intelligence behind the system. Think of like the Cuber as the channel's like vital signs. So under normal conditions, it sits at about 2 or 3%, which is a clean, healthy channel. And the moment something goes wrong, whether it be noise, eavesdropping, or interference, the Cuber rate spikes. And my system draws it at the 11% line. And above that threshold, the decision engine immediately switches to post-quantum cryptography with no delay, no drop packets, no interruption in care. And once the channel stabilizes, Cuber drops back below the safety threshold, the system reverts to QKD. It's autonomous, it's precise, and it was built specifically for environments where communication cannot go down because in hospital, it really shouldn't protect patient safety and care. So moving into the results, the first one being the Cuber, um, excuse me. And this is where the data kind of proved itself. At the baseline with no attack, Huber held steady at 2 to 3%. And under channel noise injection, it rose to 7 to 9%. Under active eavesdropping, it jumped as high as 25%. And the system responded correctly every single time with 100% fallback activation on every interception resend attack simulated. And that number matters because Cuber is not just a monitoring metric, it's a detection weapon as well. And in healthcare, environments where undetected eavesdropping could expose protected health information, a signal that is accurate 100% of the time is exactly what the system needed to prove. So going into the communication success rate, these told one of the most important parts of the story. Under normal conditions, all three protocols performed nearly identical between the 98 to 99% success across the board, which was expected. The real test was under attack, where quantum key distribution alone dropped under 60%. That's not a minor dip. That is like the system failing nearly half the time under adverse conditions. In a hospital, that's unacceptable. PQC held strong at 97%, and then the hybrid held strong as well at 96%, matching the PQC's resilience while retaining quantum level intrusion detection that PQC alone couldn't do. So you get the stability and the intelligence, and that's the value of the hybrid model. Now, going into the fallback mechanism performed with precision, 100% activation during eavesdrop scenarios, and 87% during noise injection, and 0 to 0 unnecessary activations during normal operations. The last number is just as important as the first, and adaptive systems that over triggers creates its own problems, which includes unnecessary latency, eroded trust, and performance drag. And the fact that this engine stayed completely dormant when nothing was wrong tells me that the logic isn't just reactive, but it's calibrated, and that there was no packet loss observed during any protocol transition. Interesting metrics I measured, the latency. The one honest trade-off that the data surface is the latency. The hybrid model adds roughly 10 milliseconds of overhead from the Cuber monitoring loop, the decision engine evaluation, and the protocol switching mechanism. And that brought the total latency to approximately 22 milliseconds for the hybrid model. And that is a real cost, but I think that for clinical Internet of Things devices, this framework is designed for patient monitors, infusion pumps, wearables, neurostimulators, and at 22 milliseconds, I think that's well within the real-time acceptable threshold in an environment where security is non-negotiable, and 10 milliseconds can buy you something no single protocol approach can offer, which is resilience and detection at the same time. So going into discussion and implications, just kind of like, what does all this mean? QKD is powerful in ideal conditions, but degrades sharply under real-world attacks. PQC is consistent and scalable, but it's ultimately a bet on math that hasn't been broken yet by quantum models. And the hybrid doesn't force you to choose. It hedges intentionally, amplifying the strengths of each protocol while covering the other's weakness. Now, on the implication side, the NIST is finalizing PQC standards right now via Chris Kyber or Crystal's dilithium. And healthcare organizations shouldn't wait until quantum threats are active to start planning. Infrastructure changes can take years, and the hybrid model also directly supports HIPAA compliance, providing both active intrusion detection through Cuber and a robust fallback encryption, which gives security teams a framework that is defensible today and resilient against what's coming tomorrow. So just to wrap it all up, the hybrid QKD and PQC models is the most effective framework for securing healthcare IoT in the quantum era, as it maintained a 96 communication success rate under attack compared to 60% for QKD alone. The qubit proved to be strong, reliable, and real-time intrusion detection signal, triggering 100% correctly 100% of the time. And then the latency overhead is acceptable for clinical IoT use cases. And the adaptive mechanism is precise. It fires when needed and stays quiet when it isn't. And my recommendation to healthcare IoT developers and security architects is to adopt an adaptive hybrid cryptographic frameworks now, not as a future consideration, but as a present-day design requirement as the quantum world continues to evolve. And so for future works, the simulation was validated the concept. The next step I would like to work on going into the PhD program is physical IoT test beds with real quantum channels that expanded attack models, including Trojan horse and photon number splitting attacks, latency optimization through hardware acceleration, accelerated PQC, and a formal alignment with HIPAA, NIST, FDA security guidance. And the foundation is solid, but what comes next is deployment, which is what I want to get into next through my future PhD work. And these are my references. And that was all.
Yes, the floor is open for questions or suggestions. Because quantum is the brand new in SACS, we know that we have shortcomings, but we dare to start. Thank you, Jackie, for helping these two students to learn, to make them confident. So another is coming after Mian. Thank you, Mikel. Very nice presentation.